So this is on your slide 27. I am trying to give you a real example. So you know your operational frequency is 100 megahertz. You have a 50 ohm lossless transmission line which you want to perform impedance matching to a load where the real part is 25, right? 25 is not equal to 50. You know you have to perform some kind of impedance matching. So the load is having its real part, imaginary part. Fine, let's try to work. First step, calculate your reflection coefficient correctly. First step, always calculate your reflection coefficient correctly. Once you know the reflection coefficient, right? I'm writing in a way that the reflection coefficient is having its amplitude and its phase. Okay? So once we know the reflection coefficient, we already know cosine theta prime. Right? So second step is remember forever. You have two potential choices. So now, cosine theta prime is now negative 0.62. Okay, let me just write it out for you for this problem. So when we type into the calculator, it should return one single value, but you know if your answer is in the second quadrant, you need to calculate the result in the third quadrant. Okay? So this is and the beautiful thing about cosine function is once you know the angle, the other one is the negative to it, right? So once you have this value, just add the negative sign, so you have the other angle. So this is step number 2. Try to clearly define that you have two potential theta prime angles. And then you can calculate the corresponding two distances, D1 and D2. Just erase the prime here. Okay? You don't really need a prime. So, third step, D1 and D2. Okay, so let me write down this for you. Let me divide for you. So theta prime is defined as theta gamma minus 2 beta d, which is theta gamma minus 4 pi divided by lambda times d. Okay? So d is theta gamma minus theta prime 4 pi times lambda. Okay? This is from the definition of theta prime. So D1 is, in this case, that's right. Lambda divided by 4 pi. This is somewhere you have to pay attention to. Usually from the calculators, we have the angles in degrees. When we look at lambda divided by 4 pi, this is converting the angles into radian. Okay? So this is negative . We need to convert the angles in degrees into radians. How to do that? (180 degrees is corresponding to a pi phase in radian, right? So we convert from degree to radian by this. So this is giving you the D1. The D1 is 0.063. Okay? So if we want to accomplish impedance matching, add at a distance of this from the load, we have to connect something to be defined. And second one, lambda 4 pi. This is another trick, okay? Negative 82.9 degrees minus 128.3 degrees times pi divided by 180 degrees is, pay special attention, negative. With that, right? What does a negative d stand for? A negative d stands for, we have to perform impedance matching somewhere to the right of the load. So after all these efforts, we end up with one of the solutions to be impossible. Smart students like you, do you still remember what I said in the last class? Wave impedance and therefore wave admittance are periodic. What is the periodicity? This means you have lots and lots of choices in terms of the distance where you shunt some component, right? So in this case, let's make m equals to 1, and then I'm safe. So I can almost guarantee you in your calculations, you will encounter one of the distance to be negative value. So you have to add 0.5 lambda to it, and then you're secured. Okay. So now, third step, we know the theta, we know where to perform the parallel connection. Now the point is what to be connected in parallel to. Okay? So number 4, I know my theta prime value, right? Then I can just plug it to here, and I know my PS value, right? So theta 1 prime has a BS1 value, BS2 value. So these are in the unit of Siemens. So the beauty again is once you know one answer, the other one is just the opposite sign. Okay. Number 5, I want to really convert it. Okay. What I really care about, B is the reactance, the imaginary part of the admittance. I don't like it. I'm going to flip it back into impedance, the imaginary part of impedance. So X as 1 is the inverse, and then the negative sign. I'll come to the sign part. Okay? So let's take about the value first. This 31.62 ohm is nothing more than inverse of this value in Siemens. Okay? Inverse. So why do I need to flip the sign from a negative B value into a positive X value? When you have J omega L, right? This is, for example, in the P domain, you inverse it. So you have J omega L inverted. Having this J, you have to multiply the J and J. J squared becomes negative. Okay? So remember, these are the particular tricks in dealing with complex numbers. The imaginary part will flip sign when you invert it. Okay? So a negative value of B would give you a positive value of X. So by looking at this, for distance number 1, you need to connect something in parallel, and you have a positive value. So that means ZL D1, you are connecting an inductor. Yes, question?
有人问为什么 D 错不能是负？
Oh, because you have a load, right? You have a load. For example, this is your cell phone. This is your cell phone connected to the plug. Can you perform the impedance matching by doing something to your cell phone? It's possible. You don't want to destroy your cell phone. So D is defined to be 0 from here and going positive in that direction. So if you have a negative D, it means you're doing something impedance matching to the back of your load, which is not allowed. Right? You have to open your cell phone and do something. If you're very confident, you can do it. Okay? But usually D should not be negative. D negative means it's something here. Load is our termination. Right? So we can do all the tricks before the load. Somewhere between the source and the load. This is free. But somewhere behind the load is not accessible. Is that clear? Any more question? I think the student can hear me, I think, right? I'm trying to answer. All right, so let's come back. So this. So omega L equals to 31.62 ohm. And omega C is to 31.62 ohm, right? So the first choice, at distance of D1, of course, plus integer multiple of lambda divided by 2, I can make a parallel connection of an inductor. For the second one, this is my load. D2, I can make a parallel connection of a capacitor because it's negative, right? So I know that omega times L equals to that, 1 over omega C equals to that, okay? So you might be surprised, after all this messy derivation with very bad looking numbers, beautiful results. It's almost impossible. So somewhere the textbook author really tried to do excellent work. So this is telling you at 0.063 lambda plus integer multiple of lambda divided by 2, you can connect an inductor of 50 nanohenry. Nano means times 10 to the minus 9. Pico is 10 to the minus 12. So you have two choices here. You can shunt an inductor, or at the D2 location, you can shunt the capacitor. And then you can enjoy impedance matched transmission. You have the maximum power delivered to your load. Okay? This takes work and dedication and care. What I would say is care, because I want to emphasize again. For all the impedance matching problem, you have to remember there are two potential choices, right? So one of the choice would be making parallel connection using an inductor. So you have to choose the position right. If you want to perform impedance matching using a capacitor, you will need to find the right location. Okay? So you always have two choices, inductor, capacitor. So I still have 1 minute. For the very last page, I'm not going into the details, but it will appear in your homework, and I promise you it will show up in your examination. If you still remember. If you cannot buy the inductor or capacitor, what can you do? if you still have a piece of that transmission line, like what I taught you, for short-circuited or open transmission line, for changing the length, you can change it into an effective capacitor or effectively an inductor, right? So if you cannot buy the inductor or capacitor, you can just use a piece of right length transmission line to accomplish impedance match. So with that, I'm closing the topic of transmission line. So on Wednesday, we are going to march into vector analysis, which is an easier topic for you. But somehow, for all the transmission line parameters like capacitance, inductance, resistance, we don't know how to derive up to now. So for the later part of the semester, we are going to learn how to properly formulate the transmission line parameters, right? R prime, G prime, C prime, L prime, right? So we start with a very clear guided topic, direction, and we will finish everything for the rest of the semester. Right, so do we have questions?